Hi, with Jet.
I'm Amanda Day. I'm Brianna.
I'm Joe Arrigo.
I'm Justin Rollins.
And I'm Paul Barsa.
And we are E.P.I.C.C, or Easy Propulsion in Cosmic Circumstances.
Okay, so the current system for maneuvering through outer space is a manned maneuver unit, which is extremely bulky and it's difficult to use as most of the center of mass is located in the back pack section and it can shift off your balance. So this is a diagram of more detailed components of it, and as you can see, it's extremely complicated, and all this propulsion comes from 24 thrusters that are all located in this backpack.
Currently, an MMU weighs 326 pounds, or about 147 kilograms. This not only makes it difficult to maneuver in outer space, but it also makes it costly to send into outer space because of its massive weight. As a matter of fact, this shift of the center of mass has nearly killed an astronaut on a moonwalk. As the story goes, Charlie Duke was jumping on the moon when the center of mass caused him to rotate flat on his back. He landed there, which could have damaged components that were vital for his life support systems. So he nearly died on the moon because of how heavy this was.
And so in our approach to make a better propulsion for being in the depths of outer space, we used a list of materials, namely gloves, to have a lot of gardening gloves actually, for a lot of surface area to work with, and Malar materials too. We used an Arduino Nano to upload the code and run the program that our product runs on. Touch capacitive sensors to activate and trigger the completion of a circuit when making a E.P.I.C.C. We use a continuous rotation servo, that way we didn't have to be limited by a certain angle degree. A string to pull the trigger of the compressed air can, a lot of duct tape to hold everything in place, compressed air canisters for propellant, flexible tubing to control the propellant in the direction that we're aiming for, and a tank of water and an action figure here to use as a demo. So here the tank of water represents the vacuum of space, and our little action figure here has been rigged up to a series of 2 air propulsion canisters, and as opposed to having a large pack on his back which could only rotate and move in a certain direction, he can now move his hands in the way he pleases. And using propulsion, travel forward and around, depending upon pulling certain triggers in the water. If a product like this were implemented by either NASA or any other space-faring people, it's more likely that they'd use not only 2 thrusters on their arms, but most likely 2 on their legs and 2 on their backs as well, to allow for more controlled and precise maneuvering through space. Additionally, as we mentioned earlier, these materials take up a lot less space and a lot less mass than something like an MMU would on the back, a large backpack, which again saves cost in fuel because you need to carry less mass into space. And so this is E.P.I.C.C. This is our glove that we designed through a series of wires and Arduino Nano and the compressed air canister on the back, which are all used to integrate to a closing of E.P.I.C.C. to trigger a compressed air canister.
Alright, you ready?
Yeah, and so this is
Okay,
our glove.
so here we go. Ready? No fist? Fist.
So hopefully in propellant in space, he can control the angle that he wants to.
So
and
I want to
activate.
go backwards, I go like this. To the left, I go like that, etc.
We have
And
any
so-
degree of rotation.
It's one thing for us to triumph, but now we call Dean Antoine to the stage. And then while we're getting this set up, somebody flip the slide because I'm going to explain the circuitry behind this. Somebody take the battery. Okay, so how does this thing work? So it's pretty simple. You have an Arduino Nano here, which is hooked up to a breadboard, and this is what provides all the logic and power for the circuit. And then you have 4 of these capacitive sensors, which are essentially like buttons that respond to touch. So they just detect a change in electric field because of different materials. And then when all 4 of those are triggered, which are placed on here, so your thumb has to press them like that, and then on your 4 fingers, so it detects a E.P.I.C.C., it'll complete a circuit and cause this continuous rotation servo to spin, which is hooked up to a pulley on the air can, and then that pulley spins the trigger and closes it. And therefore, you open, it doesn't do anything, and you close, it does. And Dean Antoine should be just about ready.
Shot. Check this.
were eventually able to close it at top speed. And then the second thing was the electronic components were difficult to mount, and I wish I could have a better solution for this, but duct tape solves every problem.
So our device was designed to be simple to use. All you have to do to propel yourself is make a fist. However, it's also designed to be accident-proof, which means only when all four of the capacitive sensors are touched will it fire. So pretty much the only way you can allow the device to function is if you deliberately make a fist. So this pretty much eliminates all possibilities for accidents with this device in space.
Okay, so gas tanks for our E.P.I.C.C are distributed throughout the arms as opposed to having everything in the back like with an MMU. So this more even weight distribution means for safer maneuverability and more intuitive movement for the astronaut. And in our prototype, the gas tanks represent the compressed air represents the gas tanks. That would probably be nitrogen that the astronauts would use. So plans for the future, we want to implement self-stabilization so that way the astronaut can move around more safely. And then like Luke mentioned before, we also want to have thrusters for 2 for the back, 2 for the legs, and 2 for the arms, so ideally a total of 6. And then we also want to test compatibility with other gases, such as like excess CO2 that the astronauts breathe out. And then also we want to implement variable control, so like acceleration and deceleration, so the astronaut can move around more easily.
And these are some of our references that we use. And thank you for your time. We'll be demoing these units for anyone who wants to try them. Obviously, judges give